Have you ever wondered if we could turn the tiniest organisms on Earth into, well, a microscopic cleanup crew? Today, we're diving into how scientists are literally engineering microbes to eat our most stubborn, nasty pollution.
I mean, really think about that. What if we could program them? It sounds like something straight out of science fiction, right? But it's not. This is happening right now. Scientists are giving targeted instructions to bacteria, turning them into these specialized teams designed to tackle everything from oil spills to industrial waste.
So, how in the world does this all work? Well, here's our roadmap. First, we'll get a handle on just how big this pollution problem is. Then, we're going to meet nature's original cleanup crew and dive deep into the genetic toolkit scientists use to give them a serious upgrade. After that, we'll see these super microbes in action, and finally, we'll look at what's next for this incredible technology. Okay, so to really get why we need these super microbes, you have to understand the enemy we're up against. Let's start with the problem itself, the contaminants that just refuse to go away. You know, a lot of the pollutants we've created are just incredibly tough. We're talking about compounds like PCBs, pesticides, and heavy metals. There's a reason they're called recalcitrant. They just resist breaking down naturally. These things can hang around in the environment for decades, building up in our soil and water, and posing a huge threat to wildlife and, of course, to us. So this is the core of the issue. These pollutants stick around because nature has a really hard time dealing with them. The solution, then, isn't to just wait around for nature to adapt, but to give it a powerful, well-deserved upgrade. And the big idea here is something called bioremediation. It's a pretty elegant strategy, really. We're just using living organisms, mostly microbes, to break down harmful stuff into less toxic stuff. It's basically nature's own recycling system, but sometimes it needs a little push. And that push comes in the form of genetically engineered microorganisms, or GEMs. You should think of these as the special forces of the microbial world. Using what's called recombinant DNA technology, which is essentially a biological cut and paste for genetic code, scientists can give these microbes brand new, superpowered abilities to hunt down and destroy the toughest pollutants out there. So the big question is, how do you actually build a supermicrobe? Well, let's peek inside the genetic toolkit. We're going to break down the 4 main strategies that scientists use to get the job done. All right, we're about to look at 4 really key techniques. And what's cool is they each have a totally different philosophy. We've got rational design, which is like being an architect with a blueprint. Then there's directed evolution, which is all about mimicking Mother Nature. Saturation mutagenesis, a super focused hybrid of the two. And finally, metabolic engineering, which is like building a whole new biological machine from scratch. First up, rational design. And I absolutely love the architect analogy here. With this approach, scientists need a detailed blueprint. They use their deep, deep knowledge of a protein's structure to design and build incredibly precise changes, all with the goal of making it better at its job. And the process is so meticulous, it's really amazing. Scientists start by comparing similar genes from different organisms to pinpoint the most important areas. Then they fire up computer models to predict exactly how a tiny change might improve performance. They make that one precise mutation, and finally, they test out the new and improved version. It's all completely deliberate and driven by what we already know. And does it work? Oh yeah. This is a perfect example of just how effective it can be. Using this method, scientists took an enzyme that breaks down certain nasty compounds and made it 10 times more efficient. A 10x performance boost, all through careful, deliberate design. That's a huge win. But what if you don't have that detailed blueprint? What if you're kind of flying blind? Well, that's where our second approach, directed evolution, comes in. It takes a completely different path. It's less like an architect and much more like a breeder. You create a ton of genetic diversity, and then you just let survival of the fittest do all the heavy lifting for you. This whole approach is a numbers game. Scientists will generate millions, literally millions, of random mutations of a single gene. This creates a massive library of different versions. Then comes the hard part. They test all of them to find the one that performs the best. And once they find that winner, they take it and repeat the whole process over and over, getting better and better with each round. So here's the crucial takeaway. We have 2 incredibly powerful yet totally opposite strategies. You've got rational design, the architect, carefully planning every single detail. And then you have directed evolution, the breeder, working with random chance to select for the best. Both paths can lead to some absolutely incredible results.
Okay, our third tool is a really clever hybrid of the first two. It's called saturation mutagenesis. Think of it like a locksmith's approach. Instead of trying to redesign the whole protein, scientists identified just a few crucial spots, that's the lock, and then they systematically try every single possible amino acid, every key, in those exact spots to find the one that's a perfect fit.
And the precision of this approach can lead to just mind-blowing results. In one case, it led to an enzyme with a 98-fold increase in its activity against a specific pollutant. Let that sink in. 98 times better. That is the power of finding the exact right key for the lock. And finally, we have metabolic engineering. I like to call this the master mechanics approach. This isn't just about tweaking a single part anymore. This is about building a whole new engine. Scientists take the best components, we're talking entire metabolic pathways, from different organisms and assemble them together into one single super microbe. For instance, researchers built a single bacterium that could break down certain pollutants by giving it a toolkit of 5 different pathways that they borrowed from 3 completely different types of bacteria. What you end up with is a super microbe that can do a job that no single organism in nature could ever do on its own. So we have this incredible genetic toolkit, right? But what does it all actually add up to? Let's get to the good stuff and see what these super microbes can really do out there in the real world. The applications are just astounding. We're talking about microbes that can chew through crude oil up to 100 times faster than their natural cousins, others that are designed specifically to hunt down and detoxify heavy metals like mercury, and even microbes that can neutralize the toxic parts of old herbicides like Agent Orange. This is a seriously powerful and incredibly versatile cleanup crew. Now, all of this sounds absolutely incredible, but it also raises a really important question, doesn't it? What happens to these supermicrobes when their job is done? And that brings us to our final section, the future of bioremediation. One of the most brilliant innovations for safety is the suicidal gem. How cool is that? Scientists are building biological kill switches directly into the microbe's DNA. So once the pollutant they're designed to eat is all gone, a genetic circuit gets triggered and the microbes, well, they self-destruct. They do their job, clean up, and then they disappear. It's a clean process from start to finish.
And this all brings us to one final, really powerful thought. For decades, we've been designing these tiny organisms to clean up the messes of the past. But this exact same technology could be used to build our future, creating things like sustainable materials, new medicines, or clean energy. So the real question isn't just what we can clean up anymore, it's what can we create?